First video in the Further Statistics video series will be on expected probabilities and we'll be following the format of the textbook. And so definitionally, the definition of an expected probability is the weighted average of all possible values that a random variable can take on considering the likelihood of each outcome occurring. Don't worry about this definition straight away. Think of the expected value as the mean, and the formula of such is the sum of x times the probability of x occurring. This will become a lot more clear when we delve into an example. And so the first part of the example is write down the probability distribution for a fair dice. A fair dice means that the probability of each face occurring is equal. And so if we have 6 outcomes, you can have a 1, a 2, a 3, a 4, a 5, or a 6. If they're all equal, then the probability of each occurring will be a sixth. So if we just fill in 1/6 here, we can then use our formula to calculate e to the x. So this will be pretty similar on each question. Maybe the format will be different, as in it won't tell you all the probabilities. You might have to work out some unknowns, which we'll see in the next example. But the methodology on this type of question is homogeneous. And so we do x times the probability of x for this event right here. And then for this event right here, we do x times the probability of x, and so on. One way to simplify this, when you have all probabilities being the same, you can just factor out that 1/6. So we can have 1/6 here, 1, add 2, add 3, add 4, add 5, add 6, which is equal to 3.5. So this is the basic, these are the basic steps for working out an expected probability, where the notation is e to the x. And so we'll work on a more complicated example now. So in this example, we're given e to the x and we're told to find 2 unknowns, p and q, which we can see here. And so the first step in this problem is that we need to create 2 simultaneous equations. In order to find p and q, we've got 2 unknowns, therefore we'll need 2 equations. So if we notice, these are the probabilities of each event occurring, and probabilities must always equal 1. So if we add these, and equal them to 1, we can get an equation with p and q in it. So the decimal terms add up to 0.6, add p, add q is equal to 1, therefore p add q is equal to 0.4. And then we can use the expected probabilities to work out the second equation. So for the first one, we do x times the probability of x, add 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 x times the probability of x. We can't use the same rule that we did in part 1, where we simply factored out the probability, because the probabilities aren't the same. And this is equal to 3, and we are given this in the question, e to the x equals 3. And so we can simplify this. 0.1 add 2p, add 0.9, add 4q, add 1 is equal to 3. And so this simplifies to 2p add 4q is equal to 1. We can halve this. P add 2q is equal to 0.5. And then our first equation was p add q is equal to 0.4. So if we minus, we get 0p add q is equal to 0.1. Therefore q is equal to 0.1. We can substitute q equals 0.1 back into this equation here. So p add 0.1 is equal to 0.4. Therefore p is equal to 0.3. And we can verify this by ensuring that when we sub in p and q, the probabilities add back up to 1. So 0.1, add p, which was 0.3, add 0.3, add q, which was 0.1, add 0.2, and all of this, 0.1, 0.4, 0.7, 0.8, 1. This all adds up to 1, and therefore we've completed this exercise correctly.